Last video was about the directional derivative. Right here is the definition of the directional derivative. Let's play around a little bit with this formula. So I kind of took this and put this onto this sheet right here. So this is the gradient of f evaluated p dot product with u. Let's think back to chapter 12 and about dot product and properties there. So let theta be the angle between the gradient of f evaluated at p and our vector u, the direction. So remember, what does our formula say back from section 12.3? Cosine theta, the cosine of the angle between these two vectors, is equal to the dot product of those vectors divided by the magnitude of the respective vectors here. And so if we rearrange this, if we multiply on both sides by the lengths of the gradient and the length of u, we'll have exactly this expression right here. So an alternative way to write the directional derivative is as the magnitude of the gradient of f evaluated at p times the magnitude of u times cosine theta, where theta is the angle between the gradient and u. Now, of these three things here, one of them we know exactly what it's equal to: the length of u. What's the length of u equal to? U is a unit vector by assumption, and so this equals 1. And so an even simpler way to write the directional derivative is the magnitude of the gradient of f evaluated at p times cosine theta, where once again theta is the angle between the gradient itself and our vector u. So question for you to think about: when is this the largest? So assuming that we aren't changing the gradient here, what can we change, namely that cosine theta, to make this large? And the answer is going to be, of course, we want this to be large. The biggest cosine theta can be is cosine theta is equal to 1. And when is cosine theta equal to 1? When theta is equal to 0. And so geometrically, if theta is equal to 0, what does that tell you about the gradient of f and u? This is when the gradient of f evaluated at p and u are pointing in the same direction. So just to draw a little picture here. So suppose that at this point P here, and this point P, this is the gradient f evaluated at P here. When do we get the biggest directional derivative? When we're going exactly in the same direction. When we're going exactly in the same direction here. So that needs to be our u, because the angle between u and the gradient is going to be 0. And so this gives us a lot of deep insight. This and other thoughts here are going to give us a lot of deep insights about geometric properties of the gradient. And this is going to be where the gradient just kind of goes from interesting geometric tool to something that I think you can agree will be really, really powerful. So I made up this theorem sheet here. I'm going to call this geometric properties of the gradient. It's going to run onto a second sheet here. So throughout, we're assuming the gradient is not equal to the 0 vector, otherwise that's pretty boring. U is the unit vector. Theta, as always, is going to be the angle between the gradient evaluated at P and our unit vector. So the first thing is that, I'm just recopying. This is recopied from the previous slide here. So one way we can express the directional derivative is the length of the gradient times cosine theta, where theta is that angle. So secondly, the second point here that I want to make is that the gradient points in the direction of the maximum rate of change. So what do I mean by that? So if we, so let's go back here. When is this the largest? When is this the rate of change the largest? When the gradient f evaluated at P and U are pointing in the same direction. U is unit vector in the direction of the gradient f evaluated at P. So, this just kind of tells you at a particular point. Let me just make up an example here. If at P, the gradient f is equal to the vector 1, 2, what direction gives you the maximum rate of increase? U would be, so the magnitude, the length of this vector would be square root 5, 1 over square root 5, 2 over square root 5 is the direction that gives the maximum rate of change. So that is this second point here. That's what's going on this geometric property. Okay, what about the negative of the gradient? Negative of the gradient would be what happens if we go in this direction? What happens if we go in the completely opposite 180 degrees, flip-flopped around from the gradient? Well, guess what? That's going to be the maximum rate of decrease. Perhaps I should say increase here to emphasize that we want that this is positive and this is negative here. So if the geometric meaning here is if you want to go up the hill as quickly as possible, move in the direction of the gradient. If you want to go down the hill as quickly as possible, move in the negative direction of the gradient. Okay, so we have these three facts here about geometric properties of the gradient. Okay, so two more coming up here. So the gradient is normal or orthogonal to level curves. So let me go back to the picture that I drew in the previous video right here. So let's say that we are standing at this point right here. This is pointing in the direction of maximum rate of increase here. And you can notice that that's orthogonal to the contour, the level curve. Right here, let me draw a vector that's going up the hill as quick as possible. And once again, that's orthogonal to the level curve. Here, that would be as heading up as quickly as possible. That's orthogonal to the level curve. And if you want a formal proof of that, you're walking along a level curve. Let's say that you are let's say that you're right here and you're walking in the direction of that level curve. If you're walking along the contour, your height isn't changing. So this example would here that du f of p, it would be, so this would be 0 if walking along the contour, but using this definition right here, this is equal to the gradient f value of p, the length of that, times cosine theta. If this expression is equal to 0, cosine theta must be 0. Theta is equal to pi over 2 radians, 90 degrees. So that's why the gradient is orthogonal to level curves. And then finally, if you take the magnitude of the gradient, if cosine theta is equal to 1, this gives you the maximum rate of increase, which is geometrically the maximum slope of the tangent line to z, to the surface. Z is equal to f of xy at the point p comma f of p. So these properties here, these are all really important. This shows why the gradient isn't just some kind of cute way to write down all of the derivatives in a single vector. It tells you this fact here. You know, we just managed to kick things up. Let's say we're working with two variables. We managed to go from two rates of change, partial derivative with respect to x, partial derivative with respect to y, to every possible rate of change, no matter what direction you're heading in terms of the directional derivative. And the gradient tells you how to go up the hill the quickest. It tells you how to go down the hill the quickest. And the gradient is going to be orthogonal to your level curves. All of this is very, very important geometric properties of the gradient.